Alright, day 2 of our inverse trig unit. Going to be looking at compositions of trig functions today. But let's recall what we learned last time. We want to state the domain and the range of the functions. Well, arcsine has a domain of -1 to +1. It has a range of -pi/2 to +pi/2, which means it is putting us in the first and the fourth quadrants of the unit circle. -pi/2 equivalent to 3pi/2, and then +pi/2 up top. Okay, arc cosine, same domain, -1 to +1. Range, slightly different, this time 0 to pi. Looking at the first and second quadrants of the unit circle, 0 to pi, with pi/2 right up top. Last one, arctan. This one's a little bit different than the others in that the domain is now all real numbers, and the range is also between -pi/2 and +pi/2, but it does not include those values, unlike sine. So again, we're looking in these first two quadrants, pi/2 down to -pi/2, but we are not including those pi/2 and -pi/2 endpoints because tangent is undefined there. So big, huge idea from the last lesson. With a normal trig function, the input, the thing you put into the function, is an angle, like pi/6, and the output is a ratio of sides. We're saying that the sine value, the opposite and hypotenuse of some triangle with an angle of pi/6 or 30 degrees will have the ratio of 1/2. Opposite side 1, hypotenuse 2. Well, with an inverse trig function, we're doing the opposite. This time the input is the ratio of sides, and the output is the angle. It works the other way. Regular trig, input an angle, output a ratio of sides. Inverse trig, input a ratio of sides, output an angle. They undo each other. So from yesterday, what is the arc cosine of -√3/2? Well, arc cosine uses the top half of the unit circle. Where is the value of cosine? -√3/2. Well, it's negative, so we have to be in the second quadrant there. Where is cosine √3/2? Well, that happens at our pi/6 values, which in this case will be 5pi/6. Now let's hit all of these real quick. Take a minute and do them if you will. And then let's think what they are. Arc sine of 0. Where is sine equal to 0? Well, that's going to happen at 0. Where is tangent equal to the square root of 3? That will happen at pi/3. Where is the value of cosine? -1. That's going to happen at pi. Where's the value of tangent? +1. That will happen at pi/4. Where is sine a value of a negative? Battery warning came on, was saying, where does sine have a value of a -0.5? Well, again, that 0.5, that half, is corresponding to the pi/6's, but it's negative, so we get -pi/6. And just like that, arc cosine of 0. Where does that happen? Where's cosine 0? Well, cosine is 0 straight up above at pi/2. So check yourself. Make sure you figure out where we're getting those values. And of course, we can absolutely use our calculator to figure out these values as well. Notice that on your calculator, we have the normal sine, cosine, and tangent buttons right there. And then above them, we have all the inverses in yellow or maybe in blue on your calculator. So if you want to do arctan of -8.45, you got to hit second. Then you got to hit the tan button to get the inverse. It will say tan -1 like that. We will type in -8.45. And now, depending on whether or not you're in radian mode or degree mode, and get there with the little mode button right there, and which one should you be? Well, it totally depends on the context of the problems. Oftentimes, we will be doing these problems using degrees because we'll be dealing with triangles or angles of elevation or something like that. But again, to get from one to the other, just hit that mode button and you can switch back and forth. So I'm going to calculate these in degrees. So if I do second tan to get the inverse tan up and hit negative 8.45, I will get negative 83.25. So that value is negative 83.25. Kind of an ugly angle. And that is giving us an angle in degrees. Arc sine of 0.2447, same idea. Hit second, hit the sine button, and then type in 0.2447. Your calculator will look like this. Whoops, 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 right there. And again, let's go ahead and just do this in degree mode. Second sine 0.2447, and you should get 14.164. So 14.164 degrees right there. And then finally the last one, arc cosine of 2. Well, I'm not even going to waste my time doing that because 2 is not in the domain of arc cosine. We can only have inputs between -1 and +1. So let's think real quick. What happens when you compose a function with its inverse? Well, you get back what you put in. So we know that f of f inverse of 7 should give us 7, assuming that 7 is in the domain of f inverse, and assuming that f inverse of 7 is in the domain of f, we should get 7. But what about with these trig functions? Well, let's check and make sure. Sine of arc sine of 1/2. What is that asking us to do? Well, go inside the inner function, so figure out what arc sine of 1/2 is. That's asking us where does sine have a value of positive 1/2? Well, that happens right there at pi over 6. And so then this question simplifies to what is sine of pi over 6? Well, we know that sine of pi over 6 is 1/2. So in this instance, we get back whatever it is we put in. But what about this last problem? Notice now here we have the arc sine of a sine value. And does it work the same way? Are we going to get 3 pi over 2 back out? Well, no, we can't get 3 pi over 2 back out because that's not in the range of the arc sine function. So again, think if we did the same thing, figured out what sine of 3 pi over 2 was. Well, if we did that, sine of 3 pi over 2, picture yourself a quick unit circle. 3 pi over 2 is straight down right there, which has a sine value of -1. So this question becomes, what is the arc sine of -1? Well, again, think about where we're looking. We're looking between the negative pi over 2 and pi over 2. So we need to answer this as negative pi over 2, because that's where we get a sine value of -1. Notice it's the exact same spot on the unit circle, but we have to answer in terms of our range of the arcsine function. So we have to answer this as negative pi over 2, which is a little weird, but hopefully makes sense. Alright, so let's do some of these real quick. Let's think about how they're going to work, though. Really, all we need to do is think about what is the equivalent angle in our specific range. So for the number 1 cosine problem right there, remember we're dealing with just the top half. Where is 5 pi over 3? Well, 5 pi over 3 does not fit on the top half of the unit circle, so let's think about where it actually is. 5 pi over 3 is going to happen right down here. Well, what value does that give us for the cosine function? That gives us the value, since it's at the pi over 3's right there, that's giving us a cosine of 1/2. So really this is asking what is the arc cosine of 1/2. And now we should think about just the top half of the unit circle. Where's the value of cosine of positive 1/2? Well, that's going to happen right there. Notice that's just the angle that is symmetric with 5 pi over 3 right there, flipped over the x-axis. So our answer would be pi over 3. Next one, tan inverse of tan of pi over 6. Well, pi over 6 is in the domain of the inverse tan function right there. So this time we will get out what we put in, and we will get a pi over 6 as our answer. Next one, sine inverse of sine of negative 5 pi over 4. Well, let's figure out where negative 5 pi over 4 is on the unit circle. And let's figure out then what is the equivalent angle that we need to be thinking of. Negative 5 pi over 4 says if you split this up into fourths like that, our little pi over 4 angles, which is really splitting the whole thing up into eighths, well, where do we end up if we go negative 5? So 1, 2, 3, 4. Negative 5 puts us right there, which that is not in the range of the inverse sine function, but we're looking at that value, which is a sine value of a positive, what is that, pi over 4? So positive root 2 over 2, which means on our restricted domain and range, we end up right there at pi over 4. Last one, arctan of 7 pi over 4. Well, where is 7 pi over 4? Again, that would put me right there. If we're thinking of the tangent function, tangent is defined on that interval right there, quadrants 1 and 4. What is that in terms of pi over 2 to negative pi over 2? Well, that is negative pi over 4. So, do you remember these little puzzles? These were the things where we would draw a triangle. And we would say, let's label that theta. We know sine of theta is 5 over 7, but sine is opposite over hypotenuse. And so the opposite side is 5, the hypotenuse is 7, and now we need to use Pythag to figure out what that adjacent side is. So we know this will be the square root of 7 squared minus 5 squared. I am just using Pythag and not really showing all that work, but that gives us the square root of 24, which, when you simplify, should give you, let's see, 24, I think, is 6 times 4, which means we'll get 2 root 6 as that value up there. And then we want to know what is the tangent of theta. Well, tangent is opposite over adjacent. So we're going to get 5 over the adjacent side, which is 2 root 6, which we would rationalize to 5 root 6 over 2 times 6. So 5 root 6 over 12. But we need to know, is it positive or is it negative? Well, what do we know? We know sine is positive, and we know cosine is positive. Remember, tangent is sine over cosine, so tangent has to be positive. If you think about the unit circle, all students take calculus. We know that sine is positive, so I'm in the top 2 quadrants. And we know that cosine is positive, which means I have to be in that first quadrant A, where tan is also positive. Now again, you didn't know you were doing it, but you were actually kind of doing some weird, kind of interesting inverse trig stuff right there without really recognizing it. So let's think about this. Let's solve sine of theta for sine of theta equals 5 over 7 for theta. So to do that, we need to take the inverse sine on both sides. Boom. So sine inverse on both sides. Well, the left side inverse of sine, those simplify to just theta equals the sine inverse of 5/7. Well, now think about if we plugged that into tangent of theta. Tangent of theta would then look like tan of sine inverse of 5 over 7. And so I could absolutely present this problem to you in that manner. I could say, what is tan of sine inverse of 5 over 7? And you would go about solving this the same exact way. You should draw a little triangle, and you should say, well, let's put a theta there. I know sine is the opposite over hypotenuse, so I know I get a 5 over a 7 there, because remember, When you input a value into an inverse trig function, you're inputting the ratio of sides for that trig function. Sine is opposite over hypotenuse, so I get my 5 over 7, just like I did over there. And so we know then that we could use the Pythag to get right here this value, which we said was 2 root 6, I believe. Yes, 2 root 6. And then we would say, think about literally what we're saying. We're saying that that sine inverse of 5 over 7 is that theta value. We solved it right there. Algebra says that's true. And we want to know what's the tangent of that angle. Well, the tangent of that angle is going to come from this triangle, this right triangle. And so we're going to get the opposite side over the adjacent side, which again would rationalize to what we've already found, 5 root 6 over 12. So, when you see these problems, know that really you're doing something that you already know how to do. The only thing you need to think about now that's different is that I'm not specifically telling you where you are. You need to use what you know about the functions to figure that out. What I mean is, I'm not telling you if tangent should be positive or negative. You need to think about the fact that we're dealing with the inverse sine function here, which is defined in those two quadrants, 1 and 4. You need to notice that the ratio of sides, 5 over 7, is positive, which means we're up in this quadrant where tangent is also positive. So let's do 2 of these real quick and see what we come up with. Arc cosine of 2 over 3 tells me that I'm going to draw a little triangle where cosine is adjacent over hypotenuse, so I need 2 over hypotenuse of 3, like that. And we're going to use some Pythag to get 9 minus 4 equals the square root of 5 for that opposite side. Now, what is tangent? Tangent is opposite over adjacent, so we know that tan is going to be root 5 over 2. But is it positive or is it negative? Well, think about now arc cosine. The arc cosine is positive, which means I am in this quadrant right there where tangent is also positive. Second problem here, arc sine of negative 3/5. So we draw our triangle. Sine is opposite over hypotenuse. So again, I'm going to need to use some Pythag to get 25 minus 9, which should give us 16. And so actually, I'm being silly. Didn't need to use Pythag because we have a 3, 4, 5 triangle right here. So that's kind of nice. What is cosine? Well, cosine is adjacent over hypotenuse, so we're going to get 4 over 5. Is it positive or is it negative? Well, again, think about the arcsine function. It's defined here. Cosine values are always positive there, so I get my positive 4/5. So just one last type of problem we're going to look at here. Same exact thing we just did. Notice we've got the sine of some inverse trig function of something. We're going to do the same thing, but notice this is a little goofy. It's a little different. We have a 3x in there, so a variable. But we do the same exact thing. We're going to draw a little triangle. And we know we're dealing with arc cosine, which tells us that cosine is adjacent over hypotenuse. So think of this as 3x over 1. Adjacent then is 3x, hypotenuse is 1. If we use Pythag, what do we get? Well, we get 1 minus 9x squared. How did I get that? Use the Pythagorean theorem and work backwards. Make sure you get to that spot. But now we want the sine of that theta value right there. So how do we do it? Well, sine is opposite over hypotenuse. The opposite side is square root of 1 minus 9x squared. Hypotenuse is 1, so that is just my answer right there. And think about what this is. Square root of 1 minus 9x squared. That is the equation of a circle. Or rather, in this instance, if we're thinking of it purely as a function, It's going to be a semicircle. Although it's a kind of goofy stretched semicircle that goes from positive 1/3 to negative 1/3 and all the way up to 1. So it's more like that sort of a shape. Kind of weird, kind of interesting, kind of crazy that we're dealing with only trig stuff and we get an algebraic expression. So let's do one more. Cotan of arc cosine of 5x. It's going to be very, very similar. We're going to draw our triangle. Theta equals boobity boobity. Arc cosine. Cosine is adjacent over hypotenuse. And now then, what is that side right there? That side then has to be 1 minus 25x squared. And then what is cotan? Cotan is adjacent over opposite. So we're going to get 5x over the square root of 1 minus 25x squared. So again, it's kind of messy, but this is a function that you could totally graph. We know it's going to have a 0 at 0, and we know other things about this. If you think about that square root, think about the limitations there. We need 25x squared to be greater than I'm sorry, we need that to be less than or equal to 1, because if 25x squared is bigger than 1, then we have a negative in our square root, which is not allowed. But actually, we can take it further. It cannot equal 1, because then we'll get the square root of 0, which would put a 0 in the denominator. So we get this mess, and then we can say that x squared is less than 1 over 25th, which means that x equals, or we should say x is less than, plus or minus 1 over 5 when we take the square root of both sides. Which is kind of weird when you take the square root in inequality, but really what it's saying is that the absolute value of x needs to be less than that right there. And if we're putting those abs, we can take away the plus or minus. Absolute value of x has to be less than 1/5, which is just a fancy way of saying x is less than 1/5 and greater than negative 1/5 right there. But again, not equal to. Boop. So graph it and you should find some crazy looking graph. That's it for this lesson. There's the worksheet that goes with this. See what you can come up with.